6,192 degrees Fahrenheit is the temperature at which this metal finally begins to yield to thermal destruction. Why does the modern world depend so heavily on a substance that remains solid when gold has already evaporated into the atmosphere? It only looks obvious that common metals suffice for industrial needs, but in reality, the absence of this single element would cause aircraft engines to fail and the global electrical grid to go dark. One can notice how the element number 74 maintains its structural integrity while other materials transform into liquid pools. Everything only gets more complicated further on. This rare substance is so vital that nations compete for every single gram extracted from the earth. But this is just the beginning. The industry operates with a hidden mechanical cycle where nearly 40% of the metal currently supporting global civilization has already been discarded and resurrected through advanced recycling. The process is only gaining momentum. It is visible how the discarded shards and worn-out components return to the furnace to be reborn. This cycle ensures that the tools constructing our infrastructure do not vanish after their first use. Tungsten represents a unique technical paradox where extreme heat resistance meets a constant state of rebirth. The equipment gradually processes these fragments to maintain the supply of a metal that refuses to perish under pressure. This concludes the introduction to the physical properties and the industrial life cycle of the 74th element. 3,422 degrees Celsius. This is the exact temperature required to melt tungsten, the highest melting point of any metal discovered on Earth. Why is such an extreme thermal threshold necessary for modern industry? At first glance, the requirement seems excessive, but in reality, the temperature needed to liquefy this element is sufficient to vaporize most other materials instantly. It is a level of heat comparable to the surface of a star. Only looks obvious when viewed as a static material. But this is just the beginning. At a temperature of 3,000 degrees Fahrenheit, where conventional steel would have already surrendered all structural integrity and turned into a soft mass, tungsten maintains the highest tensile strength among all pure metals. One can notice how the equipment remains stable under loads that would liquefy other alloys. It does not end at this stage. Hold a small cube of this material in the palm of your hand, and the brain becomes momentarily confused. The physical weight feels impossible for its dimensions because the substance is incredibly dense and hard. This extreme density makes it technically insubstitutable. It does not deform, it does not yield, and it does not fail in environments where any other material would be obliterated in seconds. The metal serves as the physical barrier between what humanity intends to construct and the limits of what nature allows to exist. The process is only gaining momentum. However, if this metal is capable of withstanding the heat of a furnace, the industrial effort required to extract it from the cold depths of the planet is a brutal battle. Tungsten is never found in its pure form within nature. It remains one of the rarest elements in the crust of the Earth, hidden deep inside hard rocks known as wolframite and scheelite. It is visible how the geological layers must be systematically broken to reach these minerals. 3,500,000 tons is the total estimate for the global reserves that are currently considered worth mining. This volume is nearly nothing when compared to the massive scales of iron or aluminum production, which transforms every single deposit into a critical strategic treasure. To secure this rare resource, nations such as China, Russia, and Canada operate massive mining complexes. Geologists utilize cutting-edge technology and precision sensors to locate the deep mineral veins. Once the coordinates are locked, the equipment gradually moves into position and raw physical force takes command of the operation. Boulders split with a crack as the primary extraction begins. From here, the transformation moves to the next phase of processing. Thousands of tons of solid rock shatter under the calculated force of industrial explosives. Why are these detonations necessary when excavators are already present on the site? It would seem that mechanical digging could suffice for extraction, but without the precise application of explosive energy to fracture the granite-like layers, the valuable mineral remains locked within a mass that no bucket could penetrate. Drilling rigs penetrate the earth with jewelry-like precision, creating a network of boreholes several meters deep to house the charges. Industrial explosives detonate with a millisecond delay to ensure the rock fractures into manageable segments. Colossal dump trucks weighing hundreds of tons laboriously climb from the depths of the open pit mines to the surface. One can notice how the suspension of these machines compresses under the weight of thousands of tons of ore transported every single day. This is a relentless logistical operation where every load represents a successful extraction of raw material from the crust. But the rock arriving at the processing plant is only the beginning. Transition to the next level. To convert a fragment of earth into a high-performance material, the stone must navigate a complex chemical labyrinth. It only looks obvious to use the ore as it is found, but in reality, the first mandatory stage is total destruction. Giant primary crushers and industrial mills rotate ceaselessly to pulverize the boulders. One can notice the dust settling in slow clouds as the equipment gradually reduces the stones into a fine powder. This mechanical breakdown is essential to liberate the valuable crystals trapped inside the mineral matrix. Engineers subsequently utilize the laws of physics to separate the treasure from the waste rock. By employing gravity-fed systems and potent electromagnetic separators, they isolate the valuable mineral from the surrounding debris. The resulting substance is a concentrate, though it has not yet achieved the state of pure metal. It gets more complex further on. The material then enters a series of complex chemical reactors for further purification. The equipment moves the concentrate through acidic baths and furnaces maintained at extremely high temperatures. The specific objective is the removal of every impurity at the atomic level to ensure absolute consistency. The material is roasted until it transforms into tungsten oxide, a powder that serves as the chemical foundation for every subsequent process. This stage involves dismantling the structure of the natural mineral atom by atom. One can notice how the color of the substance changes during this intense thermal treatment. The process is only gaining momentum as the production reaches the core of the metallurgical transformation. To become a metal, the tungsten oxide must undergo a reduction process to lose its oxygen atoms. This critical reaction occurs within specialized furnaces containing a pressurized hydrogen atmosphere, where temperatures rise to over 3,000 degrees. At first glance, the heat seems excessive, but it is the only way to facilitate the chemical transition. The result of this high-temperature reduction is a fine gray powder of pure tungsten. A fascinating technical detail arises at this specific stage of the operation. Because tungsten possesses an exceptionally high melting point, it is almost impossible to liquefy it using traditional casting methods. The equipment must therefore prepare the powder for a different type of structural bonding. The metal remains in its powder form, ready for the next phase of its journey. 3,400 degrees Celsius is the melting point of tungsten, a threshold so high that traditional foundry methods become impossible. Why can we not simply liquefy this metal and pour it into molds like iron or aluminum? At such extreme temperatures, no container or mold known to science would be able to hold the substance without vaporizing or losing its structural integrity. Instead, engineers must rely on the complex process of sintering to give the material its shape. One can notice how the equipment gradually compresses the fine metallic powder under crushing pressures of several tons per square centimeter. But this is just the beginning. The particles are then subjected to intense heat that brings them to the very edge of their melting point without ever reaching a fully liquid state. One can notice how the grains of powder begin to fuse into a single dense mass through atomic diffusion. It seems simple at first glance, but in reality, the bond is formed at the molecular level, creating a solid block of metal from thousands of separate particles. The process is only gaining momentum. The true industrial revolution occurs when this tungsten powder is precisely blended with carbon and cobalt to create tungsten carbide. This substance is a metal-ceramic composite and stands as one of the hardest materials ever engineered by human hands. It possesses the unique ability to cut, saw, and physically destroy almost any other substance found on the surface of the planet. Everything only gets more complicated as the mixture is finalized. With tungsten carbide at its disposal, the modern industry effectively gains a set of indestructible steel teeth. It is visible how industrial saws and cutting tools manufactured from this material slice through hardened metal alloys as if they were soft butter. In the deep earth environments of the oil industry, the durability of the equipment is tested to its absolute limit. A single drill bit containing only a small fraction of this compound can withstand hundreds of hours of friction against solid rock. The equipment gradually penetrates the densest geological layers, while the camera glides along the reinforced edges of the tool. And this is not the limit. The material maintains its sharpness even under the red-hot temperatures generated by high-speed friction. Transition to the next level of durability occurs when the carbide inserts are embedded into the heavy steel heads of the drilling rigs. The hard alloy remains unchanged while the surrounding rock is pulverized into fine dust. From here, the transformation moves to the next phase of industrial processing. Thousands of meters of solid rock and granite are penetrated by tools reinforced with this element. Why does the modern energy industry and high-precision manufacturing depend so heavily on this specific material? It would seem that other hardened alloys could suffice, but without the extreme hardness of tungsten, the extraction of resources and advanced industrial production would come to a complete halt. At first glance, this metal is a foundation for creation, but in reality, it also serves as a master of calculated destruction. In the military sector, engineers utilize the immense density of tungsten to develop armor-piercing projectiles. One can notice how the projectile maintains its shape even when hitting a target at hypersonic speeds. It does not deform upon impact. Instead, the kinetic energy is concentrated into a microscopic point, allowing the metal to punch through thick layers of reinforced steel armor with devastating mechanical effectiveness. It is the raw force of physics applied in its most lethal and concentrated form. Everything only gets more complicated as the application of the metal shifts toward preservation. In the field of medicine, the high density of this element serves a noble and protective purpose. It is integrated into the internal components of X-ray tubes and serves as the primary material for radiation shielding. Unlike lead, which possesses inherent toxicity, tungsten blocks harmful radiation waves effectively while remaining biologically safe. This ensures that both medical personnel and patients are shielded during diagnostic procedures. The equipment gradually absorbs the radioactive particles, acting as a silent guardian within the clinical environment. But this is just the beginning. The process is only gaining momentum when looking toward the aerospace industry. Tungsten alloys operate continuously within the atmospheric inferno of jet engine turbines. One can notice how the internal components remain structural at temperatures that would cause other industrial metals to liquefy or warp. Beyond its thermal resistance, the concentrated mass of the material makes it an ideal solution for balancing complex machinery. Small, dense blocks of tungsten are strategically placed within the chassis of Formula One racing cars, satellites, and commercial aircraft. The equipment gradually stabilizes as these weights adjust the center of gravity with millimeter precision. From here, the material moves to the next phase of its diverse industrial application. 100% of the tungsten used in heavy counterweights utilizes the element's extreme density to occupy minimal volume while providing vital stability. Why is this metal considered irreplaceable in environments where heat is unbearable? The answer lies in its physical properties, as tungsten literally shines in electronics within lamp filaments and conductive components that must maintain structural integrity under thermal stress. At first glance, such intensive use might seem to deplete the world's limited reserves. But in reality, the global demand is met through a sophisticated industrial loop. The process is only gaining momentum. 40% of all tungsten consumed across the globe originates from the most efficient recycling system on the planet. This material is effectively a zombie metal, possessing the unique ability to return from the dead through advanced reprocessing. One can notice how worn industrial tools and fractured drill bits are treated not as waste, but as high-value technical resources. The equipment gradually breaks these components down, and factories transform the discarded pieces back into a state of pure powder. It gets more complex further on. Because this powdered tungsten is ready to be pressed and sintered into new shapes, the cycle avoids the massive energy expenditure of traditional mining. Transitioning to recycled material is significantly cheaper and cleaner than detonating mountains to extract virgin ore from the earth. The camera glides along the production line where this infinite cycle drastically reduces environmental impact while securing a steady supply of this vital resource. This technical loop proves that high-performance technology can maintain long-term sustainability. Tungsten serves as the invisible backbone of the modern industrial era. It functions as a physical barrier that separates the possible from the impossible in engineering. This metal allows aerospace vehicles to fly higher, enables drills to penetrate deeper into the crust, and ensures that critical infrastructure operates with increased safety. Everything only gets more complicated as the material leaves the furnace, transitioning into a calm stage. Thus, the element reaches the standard ready for the further stage of its life cycle. 60 million kilometers is the total length of electrical cables that encircle the entire planet at this very second. This quantity of wire is sufficient to wrap around the Earth exactly 1,500 times. Why does a simple metal strand hidden behind a wall manage to carry enough energy to power an entire city without instantly melting? At first glance, the wire seems like a static component, but in reality, it survives a brutal journey of fire, immense pressure, and microscopic precision. The answer lies in the specialized physical properties of the material, specifically its capacity for return rather than just its hardness or melting point. The process is only gaining momentum. A drill bit piercing asphalt today might have functioned as a structural component of an aircraft yesterday. One can notice how the material resists destruction by time, yielding only to transformation through human engineering. It does not end at this stage. To illuminate a single room, the production chain must first descend into the deep darkness of the Earth. The history of every electrical cable begins far from clean or silent laboratories, starting instead within the deafening chaos of an open-pit mine. It is a location where human engineering maintains a constant struggle against the fundamental geology of the planet. Everything only gets more complicated as the scale of the operation becomes visible. The ground vibrates underfoot with a rhythmic intensity. It is not a natural earthquake, but the mechanical pulse of the industry itself. In vast copper and bauxite mines extending for several kilometers like giant scars across the crust of the Earth, titanic machines begin the extraction. One can notice the slow, heavy rotation of excavator buckets as they bite into the rock. The equipment gradually moves thousands of tons of earth to reach the ore veins. This is not the limit of the technical challenge. Heavy haul trucks with wheels, the height of 2 men navigate the steep inclines of the quarry. The camera glides along the massive ridges of the excavation site, where the transition to the next level of processing is prepared. Metal lays in its raw form within the stone, waiting for the first stage of crushing and thermal refinement. It is visible how the dust slowly settles after each movement of the heavy machinery. The material is ready to move to the next processing phase without haste. 3 stories. Exactly the height reached by hydraulic excavators that operate ceaselessly day and night in British mines. These massive machines advance over the rubble with mechanical precision. Why must engineers move entire mountains to reach the valuable ore? At first glance, the task seems impossible, but it is accomplished through a sequence of calculated industrial operations. A simple excavator bucket cannot penetrate solid geological formations, so the extraction begins with a more violent, controlled method. Engineers drill dozens of deep boreholes into the solid rock using industrial drills that penetrate the surface with jewelry-like precision down to the inch. These shafts are then meticulously filled with detonating charges according to a strict explosive map. The equipment gradually prepares for the signal. Once given, the Earth literally opens up as the calculated explosive charges detonate with a millisecond delay. Thousands of tons of rock are fractured in a single instant, and one can notice how a thick cloud of dust slowly settles, covering the entire horizon. This is the brute force required to liberate the copper and aluminum from a geological sleep that has lasted for millions of years. But this is just the beginning. The scale of the operation becomes even more immense as the primary machinery enters the scene. One can notice how the hydraulic excavators, standing as tall as 3-story buildings, extend their booms with the hiss of hydraulics. Their buckets are so vast that they could lift a standard passenger car without any visible effort. The process is only gaining momentum. These giants feed a fleet of mining trucks that function like massive mechanical monsters. Each individual vehicle carries several hundred tons of ore in a single trip across the rugged terrain. If a person stood next to one of these tires, it would be exactly twice their height. These steel giants roar along the mine roads, transporting the raw earth toward the primary crushing stations. It is visible how stones the size of large sofas are fed into the mechanisms. The boulders split with a crack under the blows of the crushers, where they are smashed like simple lumps of sugar and reduced to much smaller fragments. It only looks obvious to move the material, but this size reduction is mandatory for the ore to be sent to the refineries. Everything only gets more complicated as the transition to the next level begins. Up to this point, the entire output consists only of dirty stone and fine dust. The material is now ready to move to the next processing phase without haste. 1742 degrees Fahrenheit is the intense thermal threshold where solid mineral matter begins its total physical transformation. Why must this raw geological material undergo such an extreme ordeal of heat and electricity? It would seem that mechanical crushing might be sufficient to refine the ore. But without the application of targeted thermal energy, the chemical bonds holding the metal captive within the rock remain unbreakable, rendering the material useless for conducting electricity. At first glance, the transition from the mine to the smelter appears simple, but in reality, the mechanical brutality of extraction is replaced by a precisely controlled thermal inferno. Industrial furnaces operate at these staggering temperatures to force the raw ore to surrender its elemental form. In the specific case of aluminum production, the process manifests as a violent chemical battle within specialized electrolytic reduction cells. One can notice how the equipment gradually initiates the breakdown of bauxite-derived material. Colossal electric currents, possessing an intensity capable of instantly destroying any domestic electrical grid, are surged through the cells to tear apart molecular structures. Everything only gets more complicated. The temperature climbs steadily until it reaches 950 degrees Celsius. Under this relentless heat, the solid rock eventually yields and liquefies. One can notice how the pure aluminum separates from the waste and begins to drip toward the bottom of the deep containment tank. It forms a steady stream of liquid metal that shines with a distinct silvery luster as it accumulates. The process is only gaining momentum. For the refining of copper, the technical requirements become even more rigorous and demanding. The copper passes through series of electrolytic baths, where electricity functions as a microscopic filter on an atomic scale. This electrical force systematically strips away every single atom of impurity from the solution. It is visible how the metal gradually achieves a purity level of 99.9%. But this is just the beginning. In this industrial environment, any result falling short of that precise percentage is deemed completely. 150 tons of incandescent and purified liquid are poured into specialized steel molds with mathematical precision. Why must the cooling of this molten mass be controlled with such extreme rigor? At first glance, the process seems as simple as letting the metal rest, but in reality, any thermal deviation would compromise the structural integrity of the entire batch. Automated forced cooling systems immediately engage, systematically spraying jets of pressurized water against the exterior of the mold. One can notice how the outer shell of the metal hardens instantly under this hydraulic thermal shock, while the internal core remains extremely hot and malleable. The process is only gaining momentum. Giant rollers begin to move as the metal transitions into solid ingots, which are massive bars of material radiating an intense orange-red glow. These blocks possess the necessary chemical purity, but their physical form is entirely unsuitable for industrial application. It only looks obvious that a solid block of metal cannot yet transport electricity to a distant home or fulfill its technical purpose. It requires a complete physical transformation, which means the material will be crushed and stretched far beyond its original structural limits. The equipment gradually prepares for the next phase as the hot ingot, still emitting waves of thermal energy that distort the air, enters the automated rolling line. It gets more complex further on. One can visualize this mechanism as a heavy industrial rolling pin, but constructed from hardened steel and engineered to exert a constant pressure of hundreds of tons. The camera glides along the massive rollers as the metal appears to vibrate under the sheer force of the compression. Boulders of raw potential are forced through the narrow gap of the rolling mills, where the material is elongated and thinned as it is squeezed through the heavy mechanical roux. The molten stream goes further along the production chain. 8 millimeters is the exact thickness of the metal rod as it emerges from the initial shaping phase, having been relentlessly crushed and elongated into a long, continuous strand. Why is this specific dimension considered far too coarse for modern applications? While 8 millimeters serves as a sturdy foundation, the production of high-performance cables requires a transition into the intricate stage of wire drawing. This is the precise moment where engineering shifts its focus toward the microscopic level to achieve the necessary refinement. The rods are pulled with immense force through a sequential array of progressively smaller apertures known as drawing dies. One can notice how these dies are frequently constructed from industrial diamonds to withstand the extreme friction and pressure of the process. The velocity within the production line is staggering, with the metal racing through the machinery at speeds reaching tens of kilometers per hour. During this transit, the material is physically forced to become thinner and longer until it achieves a perfectly circular cross-section. It is visible how a thick, heavy rod transforms into a strand that is ultimately finer than a single human hair. This transition represents a state of strictly controlled violence against the molecular structure of the metal. High-precision lasers monitor every single inch of the moving wire in real time to ensure absolute uniformity. If the diameter fluctuates by as little as 1/1000th of an inch, the laser sensors detect the deviation and the automated system implements an instantaneous adjustment. The equipment gradually produces a finished wire that is exceptionally bright and as smooth as a polished mirror surface. But a hidden structural problem remains beneath this perfect exterior. It only looks obvious that the wire is ready for use, but in reality, the metal is severely stressed after being stretched and forced through the diamond dies. The internal grains of the material become rigid and dangerously brittle during the drawing process. If an operator attempted to bend the wire at this stage, it would snap with the suddenness of breaking glass. The metal requires a specific form of thermal therapy to restore its mechanical integrity and flexibility. Consequently, the strands are directed into specialized annealing chambers for controlled heat treatment. The process is only gaining momentum as the wire enters these sealed, high-technology environments. Inside these specialized furnaces, every trace of oxygen is meticulously removed from the atmosphere. This prevention of oxidation ensures the wire does not rust or degrade while being heated to the required temperature. The equipment gradually stabilizes the internal crystalline lattice, allowing the metal to recover its ductility for the next phase of manufacturing. Thus, the steel reaches the standard ready for the further stage, 600 degrees Fahrenheit. This is the precise thermal threshold to which the metallic strand is gradually heated. Why is such a specific temperature maintained with such rigor? At first glance, the wire remains unchanged, as this heat is nowhere near the melting point of the material. But in reality, this thermal energy is calibrated to allow the atoms within the metal to relax their bonds. It gets more complex further on. The crystalline structure of the copper and aluminum, which became distorted and severely elongated during the intense drawing process, begins to realign into a stable configuration. Internal tension evaporates as the metal undergoes this molecular reorganization. One can notice how the stiffness inherent in the worked metal simply vanishes. The equipment gradually feeds the strand through the heating zone, and when the wire emerges from the opposite side of the chamber, its physical properties have shifted fundamentally. Before this thermal treatment, the material was brittle and prone to snapping under pressure. Now it has become soft, yielding, and remarkably flexible. It does not end at this stage. One can observe how the wire can be bent, twisted, or coiled tightly without the slightest risk of structural failure. This invisible transformation serves as a vital thermal breath for the metal, and without it, no electrical cable in the world could function or maintain its integrity. Now that the individual strands are flexible and structurally perfect, the process is only gaining momentum. It is time to transform these components into a product that is significantly stronger than the simple sum of its individual parts. Transition to the next level. One reaches a phase that stands as one of the most mechanically mesmerizing sights in the entire industry, known as stranding. A single thin wire remains a fragile entity on its own, but the engineering goal is to unite dozens of them into a singular metallic rope of immense tensile strength. Imagine a massive machine, equaling the physical dimensions of a railway car, which sits loaded with hundreds of spinning spools of gleaming wire. The process is only gaining momentum. When the power is engaged, the operation begins to resemble a high-speed mechanical ballet. One can notice the massive body of the machine, referred to as the cage, as it starts its heavy rotation. The spools dance in perfect concentric circles, spinning so rapidly that they create a shimmering silver vortex in the air. Each individual strand is pulled with constant tension toward a single central convergence point, known as the nose of the machine. It is visible how the wires are forced into a precise twist at this junction, merging into a unified conductor. 180 layers of fine metallic filaments are layered one over the other with absolute geometric precision. Why do engineers calculate the exact angle of this helical twist down to the last degree? If the pitch of the spiral is too tight, the resulting cable becomes excessively rigid and consumes a surplus of precious metal. If the twist remains too loose, the entire conductor simply unravels during the installation process. Everything occurs in a blur of mechanical movement. It is visible how the high-speed rotors create a constant and rhythmic hum that vibrates through the workshop floor. Sensors monitor the individual tension of every single wire within the assembly. If a single strand, even one thinner than a human hair, snaps in the middle of this metallic hurricane, the equipment stops instantly. This ensures that perfection remains the only acceptable outcome for the production line. What emerges from the other side of the twisting machine is no longer a collection of loose individual wires. It is a unified conductor, flexible like a rope, strong like a solid bar of steel, and capable of carrying the massive electric current that powers modern life. But this is just the beginning. At this specific stage, the raw conductor is extremely dangerous to handle. If a person touched this bare metal while it was energized, it would result in an immediate fatal injury. The metal requires a suit of armor to function safely. Transition to the next level. Now the metallurgy of the process meets the specialized chemistry of synthetic materials. The equipment gradually guides the bare conductor into the extrusion line to receive its protective skin, known as the insulation. At first glance, this transition looks like a simple coating procedure, but in reality, it is a high-pressure chemical bonding. Inside giant silver silos, tons of small plastic granules wait in readiness. These are pellets of polyvinyl chloride, or specialized cross-linked polyethylene. They look like small decorative beads, either white or completely transparent in color. One can notice how these granules are vacuum-sucked into a machine that functions like a massive industrial-grade hot glue gun. The process is only gaining momentum. The plastic reaches its melting point as the bare wire passes through the center of the extrusion head. The molten polymer wraps around the core in an even layer, sealing the metal away from the environment. Thus, the steel and copper core is hidden within its protective shell, ready for the final stages of cooling. 100% of the raw polymer material is transformed as the extrusion machine, a giant and super powerful apparatus, begins the heating process. The plastic is subjected to intense thermal energy until it reaches the state of a viscous and homogeneous paste. Why is this precise consistency so vital for the insulation process? At first glance, melting plastic seems like a simple task, but in reality, the fluid must flow with absolute uniformity to ensure the integrity of the conductor. The metal wire travels through the exact center of a specialized steel head, where the molten plastic is injected around it under high pressure. This procedure resembles the encasing of a sausage, yet it is executed with a technical precision measured in micrometers. It is visible how the equipment maintains the plastic layer in a perfectly concentric alignment. If the insulation remains thinner on one side than the other, electricity can find a path to escape through that specific vulnerability. Such a deviation leads to catastrophic failures or the ignition of fires. One can notice the cable plunging into a long basin of cold water the very moment the hot plastic makes contact with the metal core. This transition to the next level of the process triggers an immediate thermal shock. The liquid plastic hardens instantly, locking its circular shape into a permanent state. But this is just the beginning. For larger cables designed to run beneath city streets, a single layer of protection is not sufficient. They receive additional shielding in the form of thick sheaths that are chemically resistant to oils and the sharp bites of rodents. Certain submarine cables are even equipped with heavy steel armor to withstand the crushing pressures found at the bottom of the deep ocean. The process is only gaining momentum. One might assume that the resulting product is already indestructible, but in reality, the factory does not rely on luck. Instead, the facility attempts to systematically destroy the cable before a single meter can leave the premises. Every segment must survive the intense conditions of the quality control chamber. The stakes here are extremely high because a failure represents more than a simple power outage. It could result in a hospital losing its energy supply or the start of a fire in a massive skyscraper. First, the engineers conduct the electrical test. A voltage significantly higher than what the cable will ever encounter in real-world operation is fired through its core. The equipment gradually searches for any sign of leakage or any structural weakness within the insulation layers. This is technically comparable to attempting to burst a balloon with compressed air. If the cable possesses any point of weakness, it will fail and explode here within the controlled safety of the laboratory environment. It gets more complex further on. Physical tests follow the electrical challenges to ensure the mechanical durability of the assembly. Heavy machinery stretches the cable toward its ultimate breaking point to guarantee that the metal and plastic do not separate under tension. Samples are then placed inside fire chambers to determine if the insulation can resist direct flames or if the material will fail. The molten stream of material is pushed to its absolute limits of endurance. Thus, the steel and polymer structure reaches the standard required for the final stage of industrial preparation. One can notice how the tested samples are analyzed for any microscopic signs of degradation. The metal and its protective layers move further along the production chain toward their final destination. 1,000 degrees of heat are applied to the insulating jacket to ensure the material does not melt under extreme thermal loads. Why is such destructive testing conducted on a finished product? At first glance, the cable appears complete and ready for use. However, without these trials, a single flaw in the polymer could lead to a catastrophic short circuit once installed deep underground or inside a skyscraper. Only a 100% survival rate allows the batch to proceed to the next stage of certification. Equipment gradually subjects other segments to sub-zero temperatures, freezing the insulation to verify it will not crack during the thermal contractions of a harsh winter. One can notice how lasers scan the rotating surface at high speeds, detecting microscopic imperfections that remain invisible to the human eye. The process is only gaining momentum. High-energy X-rays penetrate the thick plastic layers to confirm the metal conductor at the center is perfectly aligned and hasn't shifted during the cooling process. Finally, the approved product is wound onto massive spools constructed from reinforced wood or heavy-duty steel. Each individual reel is weighed on industrial scales, tagged with a unique identification code, and prepared for logistics. Thousands of these reels are stacked in storage yards, where they resemble giant coins belonging to a civilization of titans. It is visible how they sit in neat rows, ready to be unrolled into deep trenches, mounted onto utility poles, or threaded through the walls of buildings across every continent. The equipment gradually clears the area for the next production cycle. Everything only gets more complicated when considering the sheer scale of the global infrastructure. 60 million kilometers of cable are produced annually to sustain our modern existence. This is a global industry that generates a revenue of $200 billion every single year. One can notice the hidden complexity even in the most mundane surroundings. Look at the wall of your room at this moment. That wire concealed behind the plaster is not merely a simple combination of plastic and metal. It is a survivor of a brutal industrial odyssey. The material was born from a calculated explosion in a remote copper mine and subsequently melted in a chemical furnace at temperatures exceeding 1,085 degrees. It was drawn through the microscopic holes of industrial diamonds and cured through intense heat. It gets more complex further on. The conductor was braided in a mechanical vortex and tested with high-voltage electricity and open flames. It remains one of the most underestimated pieces of engineering in human history. These cables serve as the invisible arteries of our entire civilization. Without their constant operation, the heart of our modern cities would stop beating in a single second. The process is only gaining momentum as global demand for power increases. The next time you toggle a light switch, remember the epic journey that made that single click possible. In the world of heavy industry, even the smallest gauge wire has a massive story to tell. By 2023, the narrative of resource management took an even more unusual turn. Farmers in the Nevada desert performed an act that appeared to be financial suicide at first glance. They covered their fertile lands with 1 ton of water per acre in a radical experiment of soil saturation. Thus ends one of the key stages of heavy industrial production, where raw elements are transformed into the essential lifelines of the world. 400 times is the exact factor by which the harvest yield increased after an experimental application of pure salt. Why would a farmer intentionally contaminate the earth with a substance known to inhibit growth? Neighbors labeled the decision as madness, and agricultural specialists insisted the soil had been rendered biologically dead, yet this calculated error did not destroy the farm. In a single growing season, The sterile desert was transformed into a biological gold mine. The answer to how destroying the soil saved a multi-million-dollar industry lies buried beneath the surface, waiting to be extracted from the dirt. To grasp the true magnitude of this operational risk, one must first experience the physical environment of the region. Nevada functions as an open-air furnace where the temperature rises relentlessly throughout the day. The sun does not merely provide light in this geography. It hammers the ground until the earth forms a hard, impenetrable crust of dehydrated minerals. One can notice how the heat waves distort the horizon while the soil cracks into geometric patterns. Agriculture here is a constant war against the physical elements of the climate. At the center of this industrial battle is a crop that carries a value far higher than its appearance suggests, known as alfalfa. It seems like a simple field of mown grass when viewed from a distance, but in reality, alfalfa is a biological fortress. The plant possesses a specific mechanical secret that has frustrated agricultural technology for many decades. Each small purple flower on the alfalfa stalk conceals a brutal defense mechanism within its delicate structure. It is a physical trap designed to remain closed. Inside the petals, the reproductive column is held under extreme tension, functioning like a compressed steel spring or the set trigger of a firearm. But this is just the beginning of the mechanical complexity. Why is this physical trigger so critical for the industry? For the plant to produce the seeds that represent the financial gold farmers seek, the mechanism must be physically tripped to release the pollen. Alfalfa does not make this process easy for any organism. When an insect lands on the flower to retrieve nectar, the internal mechanism suddenly fires. The equipment of the plant reacts instantly. The column strikes the insect with a violent and surprising force as the tension is released. The process is only gaining momentum as the flower finally opens for pollination. Molten levels of heat continue to bake the fields while these micro-explosions occur across thousands of acres. From here, the transformation moves to the next phase of processing. One strike is all it takes to terrify a common honeybee, the species familiar to every farmer and biologist. Why is this mechanical impact so effective at repelling them? To an insect, it is the equivalent of receiving a punch to the face every single time it attempts to feed on nectar. These common bees, possessing high cognitive flexibility, eventually learn how to cheat the system. One can notice how they land on the periphery and pierce the side of the flower to steal nutrients while avoiding the mechanical trigger entirely. The field remains purple and visually stunning, but in reality, it becomes completely sterile. Without the physical activation of the trigger mechanism, pollination does not occur and no seeds are formed. Because there are no seeds, there is no profit for the industrial operation. Until the year 2023, this situation reached a critical threshold. 100% of potential yields were slipping away like dry sand through the fingers of the growers. Farms were losing immense capital, spending fortunes on water and fertilizers for vast plantations that physically refused to reproduce. The soil was gradually becoming more saline. Production costs escalated to levels that were practically unbearable for the industry. Modern technological solutions failed one after another in the face of this biological stalemate. It appeared to be the end of the line for the entire sector. Human technology, equipped with heavy tractors and advanced chemistry, had been defeated by the evolutionary mechanics of a single stubborn flower. This level of desperation often demands extreme measures, or perhaps a return to forgotten historical data. The solution to an impasse costing millions of dollars did not emerge from a high-tech laboratory. Instead, the answer was found within the dusty archives of a university storage room. Dr. Clara Martinez, while sorting through papers forgotten since the 1970s, discovered a specific technical drawing. It was the original blueprint of an engineer whose work had been entirely overlooked by history. One individual engineer remains the focal point of this modern industrial history, a specialist named Nomia Melanderi, commonly identified as the alkali bee. This organism bears no resemblance to the insects of popular animation. It does not inhabit communal hives, it produces no honey for human consumption, and it functions entirely without a queen. The alkali bee is a solitary subterranean worker, yet ancient records revealed an unbelievable technical capacity within its biology. It functioned as the perfect master key for the complex mechanical lock of the alfalfa flower. Evolution designed this creature with the precise physical weight and the specific behavioral courage required to activate the floral trigger. One can notice how the flower physically strikes the insect during pollination, yet the alkali bee does not retreat from the impact. It accepts the blow, collects the vital pollen, and immediately moves to the next biological target. Why did this perfect biological machine vanish from the industrial landscape? The bee was the exact apparatus the industry required, but a catastrophic problem had emerged. This engineer was functionally missing, effectively extinct, across the vast agricultural sectors of Nevada. It only looks obvious that progress would aid production, but in reality, human advancement caused this collapse. Deciduous decades of heavy plows turning the earth and the application of aggressive chemical agents destroyed the subterranean tunnels and the food sources of the species. The industry had systematically eliminated the only creature capable of preserving the harvest. Dr. Martinez identified a cruel irony in this technical failure. The solution had been present throughout history, but modern processes buried it under layers of industrialization. If the farmers intended to save their lands, they would be forced to perform an action that seemed entirely unthinkable. They had to cease their struggle against the hostile natural environment of Nevada. Instead, the process required them to reconstruct the exact habitat that they had spent 50 years attempting to dismantle. This necessity gave birth to the most contradictory project in the history of modern agriculture. To facilitate the return of the bee, farmers were required to construct a specialized habitation for the insect. This structure is composed entirely of salt. The engineering plan demanded the transformation of zones of previously productive land back into sterile deserts. It seems simple at first glance, but the process is only gaining momentum. Everything only gets more complicated as the technical requirements for the salt beds are implemented. The camera glides along the flat, white surfaces where the earth is being intentionally salinated to invite the return of the solitary worker. This marks the beginning of a structural reversal in the agricultural chain. Thus, the project moves into its implementation phase, where the environment is reshaped to meet the requirements of the biological engineer. Tens of thousands of dollars are invested in an underground irrigation network that remains completely invisible to the eye. Why would engineers install a complex system of pipes only to bury them beneath a layer of industrial salt? At first glance, this process appears to be the deliberate destruction of fertile land, but in reality, it is a calculated feat of industrial engineering designed to manipulate soil physics. The water traveling through these subterranean conduits never reaches the surface level, as its sole purpose is to maintain a constant state of moisture and softness in the deep subsoil to facilitate continuous excavation. Giant tractors maneuver across the fields with the hiss of heavy hydraulics. It is visible how the equipment gradually transforms the green landscape into a series of artificial white salt beds. The earth is first excavated to a precise depth before the irrigation grid is laid down. Following this, heavy trucks discharge hundreds of tons of industrial salt across the site. Laser-controlled graders then move across the terrain, ensuring the surface is flattened to the exact specifications of a billiard table. One can notice the machine blades rotating ceaselessly to achieve a perfectly level crust. Everything only gets more complicated as the chemical properties of the salt begin to function as a thermal regulator. The salt layer draws moisture from the damp subsoil toward the surface through capillary action, creating a hardened white shield that provides total thermal control over the environment. To any observer traveling along the nearby road, the scene resembled a descent into madness. Local media outlets labeled the project a bizarre experiment, while neighboring farmers often stopped their vehicles to witness what looked like the intentional creation of a dead zone. But this is just the beginning. The high cost of creating these brilliant white expanses in the middle of lush farms was a calculated risk, representing the only remaining technological bet for the landowners. The stage was set, reflecting the intense rays of the sun, awaiting the arrival of its intended inhabitants. The day of release served as the ultimate moment of technical truth. Specialized transport trucks arrived at the perimeter carrying heavy crates, though these containers held no electronic components or machinery. The material is delivered to the site, marking the transition to the next phase of the operation. Millions of dormant alkali bee larvae arrived in trucks carrying massive blocks of soil and earth. Why was such a primitive delivery method chosen for such a high-stakes project? It would seem that delicate insects would require sophisticated transport containers. But in reality, the natural soil provided the exact thermal insulation and humidity necessary to keep the larvae alive during the transition. The laborers simply dumped the entire cargo onto the salt-crusted ground. One can notice how the dirt piles settled in the heat without the presence of wooden hives, protective netting, or beekeepers in specialized suits. This scene appeared anticlimactic to skeptics, yet terrifying to those who had provided the capital. Only millions of insects were left exposed on the hot saline desert floor as the sun beat down. But this is just the beginning. Public opinion shifted toward mockery as footage of the dumping spread, leading many to predict the total destruction of the larvae within 48 hours. Critics claimed the intense desert heat would cook the insects where they lay. During the initial days, a heavy silence hung over the site, and the white surface of the desert remained completely motionless. It seemed as though the entire financial investment had evaporated into the dry air. At first glance, the lack of activity signaled a total loss, but in reality, the biological process was merely entering its most critical phase. Tension on the farms became physical as the risk of public humiliation grew alongside the potential for massive financial ruin. Headlines in local newspapers focused on the perceived madness of the Nevada project and its imminent failure. It gets more complex further on. Below the hostile crust of salt, out of reach of cameras and the eyes of critics, a biological revolution was already starting to unfold. The underground army was beginning to wake from its slumber. While the world watched the surface for signs of life, one of the most significant works of biological engineering on the planet was accelerating beneath the dirt. The equipment of nature operates differently here, as alkali bees do not merely dig holes, but construct complex subterranean cities. Within the darkness, the moisture levels were held in a perfect state by the hidden irrigation system. The process is only gaining momentum. Each female bee functions as a high-precision mining unit. It is visible how they begin to carve out perfectly round vertical shafts that descend to a depth of 50 centimeters into the earth. The precision of these tunnels is mathematical, ensuring the stability of the entire colony structure. From here, the transformation moves to the next phase of processing as the insects establish their permanent domain. 1,000 square meters of salt-encrusted ground serve as the foundation for an engineering marvel hidden beneath the surface. These insects utilize the natural moisture of the soil to cement the walls of their tunnels, meticulously constructing smooth and resilient tubes that resist collapse. This structural integrity ensures the survival of the colony against the shifting pressure of the earth. But why is the moisture levels of the substrate so critical for the architectural stability of the nest? Water acts as the primary binding agent for the fine particles of the desert floor. This simple interaction between liquid and earth creates a reinforced lining that allows the intricate network to expand without the risk of structural failure. The crust of salt covering the surface, once criticized for its perceived infertility, functions as a perfect thermal and defensive shield. One can notice how the crystalline layer reflects excessive solar heat away from the subterranean chambers, maintaining a stable internal climate. It is visible how the hardness of this mineral barrier prevents predators, such as ants and beetles, from penetrating the tunnels. The salt essentially operates as a castle wall, impenetrable to those without the specialized tools to breach it. But this is just the beginning. The population density of this underground environment defies conventional urban logic. Thousands of individual nests operate side by side within a single square meter of salty ground. Everything only gets more complicated as the scale of the colony increases. This creates an invisible high-density metropolis where every centimeter of space is utilized for the survival of the species. Inside each tunnel, specialized brood chambers are constructed and lined with a natural waterproof secretion. This substance seals the walls, protecting the stored pollen and delicate eggs with the security of a bank vault. Day after day, the city continues to expand beneath the feet of observers. Where human eyes saw only white, dead earth, life was in reality teeming on a massive scale. The process is only gaining momentum. Human infrastructure, including pipes and leveled ground, provided nothing more than the initial foundation for this biological expansion. The bees acted as the final architects, and when the construction phase reached its conclusion, the city opened its gates to the world. At first glance, the transformation appeared gradual, but in reality, it manifested as a sudden explosion of activity. Weeks after the initial release of the site, the surrounding alfalfa fields began to vibrate with physical energy. A deep, heavy, and constant hum filled the atmosphere as millions of alkali bees emerged from the soil simultaneously. The equipment of nature was now fully operational. These insects did not emerge for leisure, but to fulfill a specific biological role within the ecosystem. The molten stream of life moves further along the production chain without haste. 1,200 kilograms of alfalfa seed per hectare is the staggering volume achieved by utilizing the alkali bee. Why did the productivity of these fields undergo such a radical transformation? The answer lies in the mechanical efficiency of these insects, which far surpasses the capabilities of common honeybees. High-speed cameras recorded every millisecond of the brutal interaction between the insect and the plant. One can notice how the alkali bee lands on the blossom and applies a precise amount of pressure to the petal structure. Suddenly, the flower trigger is activated with a physical impact that strikes the bee directly in the chest. The insect absorbs this blow, collects the released pollen, and transitions to the next flower in a fraction of a second. But this is just the beginning. These biological machines function with programmed precision, exhibiting no hesitation or deviation from their specific task. The rate of pollination accelerated by a factor of 2, then 3, changing the landscape in real time. It is visible how the purple blossoms began to wither rapidly across the fields. This serves as the universal physical indicator that successful pollination has occurred within the plant structure. Seed pods began to swell under the weight of the developing yield, physically bending the green stalks toward the earth. The process is only gaining momentum. Farmers observed the transformation of their crops with total disbelief as the season progressed. When the heavy harvesters finally entered the fields at the end of the production cycle, the industrial data confirmed a massive shift. Productivity did not merely increase, it spiked to unprecedented levels. In regions where the historical average previously fluctuated between 300 and 400 kilograms per hectare, the output reached 1,200 and even 1,300 kilograms. This represents a total increase of 300 to 400%. At first glance, the initial investment in the salt beds seemed excessive, but it was fully recovered during the very first harvest. The high-stakes industrial gamble had successfully bypassed traditional limitations. It gets more complex further on. Nature, utilizing its ancient and physical mechanics, outperformed modern chemical applications and heavy machinery by a significant margin. If the camera glides over the Nevada desert today, a distinct visual phenomenon becomes apparent. Bright, geometric white squares cut through the continuous green expanse of the agricultural zones. These structures only look like scars on the land, but in reality, they are functional monuments to biological intelligence. We have become accustomed to the idea that industrial progress is exclusive to the development of microchips, drones, or sterile laboratory environments. Everything only gets more complicated as the scale of production increases. In this specific region, the industry integrated a lesson regarding the power of natural systems. The material is ready to move to the next processing phase without haste. Thus ends one of the key stages of this biological production cycle. 11,200,000 tons of oysters are produced by a single nation in just 12 months. Why does this massive industrial output create an environmental crisis alongside a culinary triumph? One might assume the shells are simply returned to the sea, but in reality, the sheer volume of calcium carbonate waste overwhelms the local ecosystems. 8 out of every 10 oysters served in luxury establishments from Paris to New York originate from this specific maritime border. Yet the logistics of managing the remains of this global feast are only getting more complicated. At first glance, the coastline of 11,200 kilometers looks like a pristine source of protein. The process of oyster cultivation has transformed this entire maritime frontier into the largest protein factory in the world. It is visible how the scale of production dwarfs the combined output of industrial giants like the United States and Japan. Everything only gets more complicated when the meat is removed, leaving behind white mountains of waste that refuse to decompose naturally. One can notice how these calcium ridges accumulate in massive piles along the shores, where they begin to rot and release toxic gases into the atmosphere. The equipment moves with a mechanical rhythm, but it cannot keep up with the rate of accumulation. It seems simple to dispose of shells, But in reality, these mountains of waste poison the air and occupy valuable land. This industrial paradox creates a situation where a luxury delicacy results in a deadly environmental footprint. But this is just the beginning of the transformation. The very material that threatens the air is the only known cure for agricultural soil that has become as acidic as lemon juice due to intensive farming. Millions of dollars in additional seeds are the direct result of returning these minerals to the earth. The nature of the solution requires the audacity to trust a biological design that has undergone millions of years of field testing. The process is only gaining momentum as engineering finds a way to grind and treat these shells to neutralize soil acidity. One can notice the dust settling in slow clouds as the hammer crushers break down the calcified structures into a fine white powder. This white gold is then redistributed across the fields to restore the chemical balance of the terrain. Humility is required to acknowledge that the most advanced engineering often involves returning to natural cycles. The equipment gradually processes the mountains of waste, turning a catastrophe into a vital resource for global food security. It only looks obvious to discard the shells, but the wisdom of reclaiming this material allows for a leap into a more sustainable future. This concludes one of the most significant cycles where industrial waste is reclaimed to save the dying soil. From here, the material enters a new phase of utility, moving through the production chain to support the next harvest. 90% of the oyster consists of a calcium carbonate armor as hard as stone, a biological reality that remains relentless in regions like Japan and France. While the animal is harvested for its edible flesh, that meat represents a mere 10% of the total biological mass. Why does this physical disproportion create such a severe environmental crisis? At first glance, a shell seems like harmless organic matter. But in reality, these structures take several centuries to decompose naturally, resulting in a colossal waste stream that the ecosystem cannot absorb on its own. 6,600,000 pounds of shells are discarded every single year as a direct consequence of this industry. The shells do not simply disappear into the environment after the harvest is complete. Instead, they accumulate along the coastlines of the Fujian and Guangdong provinces in massive, unmanaged quantities. One can notice how new geological formations have emerged across the landscape, appearing as artificial mountains of bleached white shells that reach several meters in height. But this is just the beginning. The equipment used for transport can barely keep pace with the sheer volume of mineral waste being deposited daily on the shoreline. Under the heavy, humid heat of the summer months, these white ridges transform into unintended chemical reactors of decomposition. It is visible how the residual organic tissue trapped deep within the jagged crevices begins to rot, creating a breeding ground for rapid bacterial proliferation. The process is only gaining momentum as the sun beats down on the piles. Invisible clouds of ammonia and hydrogen sulfide are released from the gaps between the calcium carbonate layers. The air becomes physically toxic, acting as a severe irritant to the lungs of local residents who live in the shadow of these mountains. This chemical runoff leaches into the surrounding environment, oxygen levels drop, and the water quality in nearby lakes degrades until it kills the fish populations used by the community. Thus, the material remains in a state of stagnant decay, awaiting a technical solution to break the cycle of accumulation. 3 8/10 to 4 2/10 is the critical range where the pH level of the fertile soil in Fujian has plummeted. Why has the earth in this region become a wasteland of desolation? This chemical shift has turned the ground into a medium nearly as acidic as pure lemon juice, creating a landscape where life struggles to persist. At first glance, the terrain appears normal, but in reality, the soil is dying from a total exhaustion of nutrients just a few kilometers away from the coast. Agricultural orchards in 2021 presented a scene of absolute desolation to any observer. One can notice how the earth is cracked and devoid of vitality, appearing dry even in humid conditions. The acidity has reached such a hostile state that the roots of the fruit trees are effectively burned upon contact with the earth, losing their ability to anchor themselves in the substrate. It only looks obvious that rain would provide relief, but the water no longer penetrates the surface. It is visible how the rainfall simply slides across a top layer that has become hard and impermeable, mimicking the properties of wet cement. The local authorities have officially recognized a terrifying reality regarding the future of these provinces. Without immediate intervention, vast expanses of traditional cultivation areas face complete abandonment in less than 15 years. On one side of the geographical equation, mountains of calcium waste are poisoning the atmosphere, while on the other, acidic lands are suffering from a desperate lack of that very same element. The solution seems simple, but it requires a colossal feat of engineering to bridge these two environmental disasters. This is not the limit of the challenge, as the logistics of connecting a toxic surplus with a critical deficit demand a massive industrial scale. The answer did not emerge from a futuristic invention, but rather from the industrialization of an ancient concept. Engineers identified that those foul-smelling mountains of discarded shells were actually concentrated mines of pure biological limestone. To transform this toxic residue into a restorative medicine for the earth, the construction of a giant machine became a physical necessity. The process is only gaining momentum as the infrastructure rises to meet the crisis. In the city of Ruyan, a massive factory was erected with a singular and precise mission. The equipment gradually fills the landscape, marking the transition from ecological decay to industrial recovery. This facility serves as the primary link in a chain designed to neutralize acidity and recycle waste into a vital resource. Thus, the foundation is laid for a transformation that aims to restore the chemical balance of the region. 264 million pounds of oyster shells are consumed by industrial processing plants every single year. Why is such a massive volume of calcium-rich waste subjected to these extreme mechanical and thermal forces? At first glance, the task appears to be a simple matter of disposal, but in reality, the facility must transform biological waste into a high-precision agricultural tool. Heavy dump trucks discharge the raw, jagged shells into industrial crushers where the initial limestone structures are shattered into smaller fragments. The equipment gradually breaks the material down under immense pressure, preparing it for the heat. But this is just the beginning. The crushed shells are fed into gigantic rotary kilns for a thermal process known as calcination. One can notice how the long steel cylinders rotate ceaselessly to ensure the material is exposed to the heat from every angle. Inside these chambers, the temperature climbs steadily until it reaches 473 degrees Fahrenheit, which is exactly 245 degrees Celsius. The material remains trapped in this controlled inferno for 30 minutes. This duration is calculated with precision to ensure the physical properties of the calcium carbonate are altered. It gets more complex further on. Intense heat serves two vital functions within the production cycle. First, it achieves absolute sterilization by ensuring that any harmful bacteria or residual organic matter is incinerated instantly. Second, the thermal energy restructures the shell on a physical level, making it brittle and easier to pulverize into a microscopic consistency. One can notice how a fine white powder, known as oceanic biocalcium, emerges from the discharge end of the line. It is visible how the cooling systems manage the heat as the dust settles into collection bins. This substance is not merely crushed stone, but a mineral-rich soil conditioner designed to restore the exhausted lands of Fujian. For decades, these fields have suffered from severe nutrient depletion and rising acidity. The powder functions as a natural antacid for the earth itself. It is visible how the powder neutralizes soil acidity upon contact, much like a chemical buffer. This reaction unlocks essential nutrients that were previously trapped in the acidic ground, fostering an environment where biological life can thrive. The process is only gaining momentum. 220 million pounds of clean, high-grade agricultural product now exist, where there was once only toxic biological waste. The transition from discarded shells to a vital resource is now complete. The refined powder is moved toward the packaging stage, ending this phase of the mineral transformation. 300,000 rural families stand at the threshold of a shift that is far more than a mere technical upgrade. Why did the introduction of a simple biological byproduct trigger such a massive economic revolution across the countryside? It would seem that standard chemical fertilizers should have been sufficient to maintain the stability of the local food supply. But the reality is that the soil had reached a state of acidic exhaustion that traditional industrial methods could no longer rectify, leaving the land in desperate need of a structural resurrection. The theory appeared sound on paper, yet the practice of agriculture remains a volatile and unpredictable field of battle. One can notice the heavy trucks arriving at the devastated farms, their beds filled with the processed oyster shell powder. This material was bagged and ready to protect the upcoming harvests from further degradation. The true trial for this recycled resource began the moment it was integrated into the earth. It only looks obvious that adding minerals would help, but in reality, the speed of the transformation challenged the expectations of even the most skeptical scientists on the project. The first major success manifested in the scallion fields, which represent a vital crop for the entire regional economy. In areas where the plants were previously yellowing and stunted due to nutrient lockout, the application of the powder triggered an immediate biological recovery. Productivity in these specific sectors climbed by nearly 60%. This means 60% more food was harvested from the exact same acreage without the introduction of a single additional gram of synthetic chemical fertilizer. The process is only gaining momentum. In the grapefruit orchards, the observed changes were both chemical and structural in nature. One can notice how the leaves transition back to a vibrant, deep green as the internal health of the trees stabilizes. Sensors buried deep within the soil profile recorded that the pH levels rose by 1.1 points, effectively moving the substrate out of the acidic danger zone. This shift was accompanied by a 28% increase in organic matter, which functions as the primary fuel for all biological life within the soil. Trees ceased the premature dropping of their fruit, allowing the crop to reach full maturity on the branch. At first glance, this was a victory for the land, but in reality, it was a triumph for the farmers' financial stability. An experimental trial with lettuce revealed a series of unexpected data points regarding the quality of the final product. Plants cultivated with the shell powder did not simply increase in physical volume. It is visible how the leaves become more structurally sound, resulting in a crispness and sweetness that surpassed traditionally grown varieties. Chemical analysis confirmed that these plants were significantly richer in vitamin C than those treated with standard industrial chemicals. Everything only gets more complicated when the market dynamics are factored in. Wholesale prices for this high-quality lettuce rose between 12 and 18% as buyers recognized the superior nutritional profile. For the local families, this meant a complete restructuring of their profit margins. The cycle appeared to have been closed with mechanical perfection as the waste from the sea became the lifeblood of the field. From here, the transformation moves to the next phase of processing. 37.5 billion pounds of peanuts are harvested by China every single year, cementing its position as the largest global producer of this critical strategic crop. This massive agricultural output suggests a landscape where the sea once saved the land and the earth in turn rewarded human labor. Why did the application of miraculous oyster shell powder to degraded peanut fields lead to a frustrating and unexpected mystery? It would seem that enhancing the soil would automatically increase the yield. But as the scientists soon discovered, nature does not function as a machine that obeys human desires without resistance. The ecosystem only looks simple on the surface. One can notice how the soil structure improved chemically after the intervention, with the acidity levels dropping as the pH rose and the earth becoming physically softer to the touch. But despite these ideal mechanical conditions, the harvest volume began to decline sharply. At first glance, this contradiction defied logic, yet the secret was hidden within the microscopic world of the root systems. But this is just the beginning of the technical challenge. Peanuts belong to the legume family and survive through a complex symbiotic partnership with specific bacteria inhabiting their root nodules to capture nitrogen directly from the atmosphere. The rapid shift in soil alkalinity triggered by the calcium-rich oyster powder acted as a biological shock to these sensitive microorganisms. They were physically unable to adapt to the high velocity of human chemical intervention within a single growing season. It gets more complex further on. This outcome served as a brutal lesson in humility for the field of environmental engineering. One can notice how the biological pace of the microorganisms dictates the success of the entire nitrogen fixation process, regardless of mechanical soil quality. It is visible how the ecosystem requires a specific duration to recalibrate its internal balances. It only looks obvious that a soil additive would work instantly, but in reality, biology cannot be rushed by industrial schedules. The oyster shell powder proved its immense power, yet it was clearly not an instant magic wand applicable to every plant species without careful timing. While the research teams learned the necessity of technical patience on the Earth, another group of experts began to turn their focus back toward the aquatic origins of the material. The process is only gaining momentum. From here, the investigation shifts its trajectory to where the entire cycle originally started. 85% of the natural oyster reefs in this coastal region have vanished entirely over the course of the last 150 years. Why did the underwater ecosystem collapse so drastically? At first glance, the ocean surface appears unchanged, but beneath the waves, the seafloor transformed from a vibrant living forest into a barren desert of silt and mud. The crisis extended far beyond the massive piles of discarded shells accumulating on the shore. But this is just the beginning. Engineers and biologists bypassed modern industrial solutions, choosing instead to travel back in time to adopt a strategy from 300 years ago. It seems simple to look toward the past for answers. In reality, the restoration of this lost world required no high-strength concrete or complex metallic frameworks, relying instead on the ancient wisdom of previous generations. One can notice how workers drive simple bamboo stakes and wooden poles manually into the thick mud of the coastal flats. The process is only gaining momentum. Without the intervention of heavy machinery, these vertical structures are positioned to harness the natural force of the tides. This creates a stable foundation for the microscopic oyster larvae that float suspended in the water column. Everything only gets more complicated as the biological cycle takes hold. Because these free-swimming larvae require a solid surface to attach themselves to, the wooden stakes serve as the essential anchor point for their survival. It only looks obvious that life would return, but the speed of the recovery surprised even the most experienced specialists. Within only a few months, the equipment, in this case the natural timber, was completely submerged under thick layers of new oysters. The biomass in the designated restoration zone increased by a factor of 10. The process does not end at this stage. One can notice the physical change in the water quality as the reef expands across the formerly empty mudflats. A single adult oyster functions as a sophisticated biological filtration machine. The camera glides along the newly formed clusters, where the mollusks pump water through their systems ceaselessly. But the true power of these reclaimed reefs is not merely providing a habitat for marine life. This biological mechanism cleans the surrounding environment with a level of efficiency that artificial systems cannot replicate. The transformation moves to the next phase as the water clarity begins to improve across the entire estuary.